This lecture is about the idea of pressure in physics. Pressure is the force applied per unit area on a surface. The variable is lowercase p, and the unit is Newton per meter squared, or PA, which is short for Pascal, who was a famous mathematician and philosopher who worked a lot with the idea of pressure. The equation for pressure is just force over the area that it's applying on. Pressure is a scalar quantity because information about a material's pressure does not tell you which specific direction force applies. Material with a given pressure always applies a force pointing away from itself. As an example, we can imagine that this green gas is at 10 pascals of pressure and it's contained in this black box where each side has a surface area of 2 meters squared. Because pressure is equal to force over area, the force applied by the pressure is equal to the pressure times the area. So because each side of the box has an area of 2 meters squared, the force on each side of the box is going to be 20 newtons. So the gas in this box is applying an outward force of 20 newtons on each individual surface of the box. And you can see that the force it's applying is not just applying in one specific direction. It's not just applying up or down or left or right. It's applying outward everywhere. So because the forces from the pressure apply in multiple directions, the pressure itself does not have a direction, so it's a scalar, not a vector. Doing math with the pressure equation by itself is very simple. I'm just going to throw up these 4 examples. I'm not even going to talk through them. I'll just display the problem-solving process. There are some pressure problems where you have to calculate the area the pressure is applying to. In problem 3, you're given a circle of radius 5, so you just have to know that the area of a circle is 2 pi times the radius squared. And in example 4, you're given a rectangle with a length of 0.2, and you need to calculate its width. So geometry comes into pressure equations at times. Example number 5 has some more complex geometry, so I want to show you how that works. A solid cylinder of height h and density rho is placed on a flat surface. Show that the pressure P exerted by the cylinder on the surface is equal to rho times g times h. So the pressure is the force over the area, and I know that the force applied by the cylinder, because it's resting on a surface, its force of gravity is pulling it into that surface, so the surface has to support it with that same force. So that means the force it's applying is equal to the mass times the acceleration of gravity. And I know that mass is equal to density times volume because density is equal to mass divided by volume. So if I rearrange that equation, that's what I get. And I know that the volume of a cylinder is equal to the surface area of the base of the cylinder multiplied by the height of the cylinder. So I can now take this volume back and plug it into my mass equation, and then take that mass equation and plug it into my force equation, and then take that force equation and plug it into my pressure equation. And when I do that, I can see that the areas cancel out. And I can see now that the pressure is equal to the density multiplied by the height of the cylinder multiplied by the acceleration of gravity. As a rule, if there's any kind of difference in pressure in gas in a container, gas always flows from a higher pressure to a lower pressure region until the two pressures are equal and the pressure is equally distributed everywhere around the container. We can imagine that gas 1 and gas 2 are in 2 containers connected by a tube that the gases can move through. If the problem says the gases do not move through the tube, this tells you that they have the same pressure as each other. You can assume, unless otherwise stated, that all regions of a gas always have the exact same pressure as all other regions of a gas. Because pressure is equally distributed, we can use proportional reasoning to find the force applied on different parts of the container of pressurized material. An example here says the area of the top and base of a box is A, and the other sides have area 2A. The force from pressure inside the box is 20 newtons on the top of the box. What is the force on any one side of the box? I know that pressure is force over area, so therefore force is equal to pressure times area. So we know that 20 newtons is equal to the pressure inside of the box multiplied by the area of the top or base of the box. And I also know that that pressure is the same everywhere in the box, so it's being distributed to all parts of the area. So if I want to know the force on one of the sides of the box, I can use the same pressure but this new area. And when I isolate my original equation, PA, I can plug in 20 newtons because I know PA by itself is 20 newtons. So altogether, I can see that 40 newtons are applying to any one side of this box. I can use proportional reasoning and the fact that pressure is constant in all parts of the container to predict missing forces on the object. If there's a difference in pressure on two sides of a barrier, we can calculate the force on each side. I can pretend that we're looking at this barrier from the side, and altogether its surface area is 5 meters squared. So the pressure on one side I'm going to say is 10 pascals, and on the other side there's a pressure of 4 pascals. Again, using pressure equals force over area, and rearranging to find force, if I multiply the pressure by the area, I'll get the force applied. So the force applied from the green gas is equal to 20 newtons to the left, and the force applied from the blue gas is equal to 50 newtons to the right. So I can see that the net force on this barrier is 30 newtons to the right. So these forces behave just like other forces. We can add them together to find the net force. A common pressure problem asks how much force it would take to open a door with different pressure on either side. A door is prevented by its frame from opening in one direction. The force required to open the door is equal to the difference between the two forces from the gas pressure. So we can pretend that this barrier is a door. You can see that it has a door frame on one side of it that puts a force on it, preventing it from accelerating to the right. That force perfectly balances out any other forces pushing into it, so altogether the net force is 0, so the door does not accelerate. The door frame is applying this 30 Newton force to the left to prevent the door from moving into the frame. So if we want to open the door, we have to apply a force of pull to at least completely cancel out the force of the door frame, and then add a little bit more to make the net force no longer 0. So if any additional force is applied from this point, the net force will be non-zero and point away from the door frame, and the door will begin to move. Therefore, the force required to make it move is equal to the difference between the forces given by each pressure, which here is equal to 30 newtons. If one pressure is pointing to open the door with 20 newtons, and the other pressure is pointing to keep the door closed with 50 newtons, altogether it would take an additional 30 newtons of pull or more to open the door, but 30 newtons is the minimum required. Air in Earth's atmosphere also has pressure, so if a material is exposed to the air with no barrier between it and the air, atmospheric pressure applies on it. As an example, a tube holds air compressed to a pressure of 1.1 times 10 to the 5th Pascal by a cylinder with a mass of 500 kilograms and a base of 0.5 meters squared. The only thing supporting the cylinder is the pressure from the air, and we want to determine the atmospheric pressure of the air outside the tube. I'll draw a free body diagram to figure this out. So I know that there's the force of gravity on this object pulling it down, which is equal to 4,900 newtons because it's mass times the acceleration of gravity. There's also an upward force from the pressure inside the tube, and that force I know is equal to the pressure times the area, which is equal to 5.5 times 10 to the 4th newtons. And because there's air with pressure above the blue object, that pressure must also be pointing down on the blue object. So that force is going to be equal to the atmospheric pressure of Earth multiplied by the area that it's applying to. I also know that because this mass is not accelerating up or down, it's just standing still, the net force must equal 0 as a result. That means that these three vectors added together have to equal 0. So when I write out the equation like this, I now have an equation with only one missing variable, so I can isolate the pressure of the atmosphere, and when I do that, I get 1.0 times 10 to the 5th Pascal. Those are all the facts about pressure that you'll need to solve problems with just that concept. It's going to become much more important when we start working with the ideal gas law, PV equals nRT, in a later lesson in this unit.